Entropy, a property of a system. By applying the equation 8.1, inequality of Clausius, and consider this picture, we can demonstrate that the second law of thermodynamics leads to a property of a system that we call entropy. Second law of thermodynamics leads to a properties of a system that called of a system that called entropy. Let a system undergo a reversible process from 1 to stage 2. Along a path A, and let the cycle be completed along path B. So we have a cycle here, which is also reversible. We can write A and B are reversible because this is a reversible cycle. We had B. Now consider another reversible cycle from A to B. From A and reverse was B, C. We can write for A and C, C and B. Are reversible duration of by subtracting these two equality, we have 0 equals to A minus 1/2 second C. As a result, we can write that Same, since the on T is the same for our reversible path between state and 2, we conclude that this quantity is independent of path and is a function of the end and the state only. Since integration is same for our reversible path, between the state of 1 and 2 as previously between example state 1 and 2, we conclude that this quantity is independent. Conclude path and is a function of the end state. State only. It is therefore a property. This property is called the it is therefore the property. This property is called entropy. And is designated as S. It follows that entropy may be defined as a property of a substance in accordance with this relation. ds for reversible process. Entropy is an extensive property and the entropy per unit mass is designated as large as S. It is important to note that entropy is defined here in terms of reversible process. To change the entropy of a system to undergo the change of state may be formed by the integration as reversible S2 minus S1, the integration of for reversible process. To perform this integration, we must know a relation between T and Q, and illustration will give it subsequently. The important point is that since entropy is a property, The important point is that since entropy is a property, the change in the entropy of a substance in going from one state to another is the same for all processes. From one state to another is the same for all processes. Both reversible and irreversible. Between these two states. This equation enables us to find the change in entropy only along a reversible path. Is for reversible. However, once the change has been evaluated, this value is magnitude of the entropy change for all processes between these two states. This equation also enables us to calculate change of entropy, but it tells us nothing about absolute value of entropy. The equation is for change in entropy, not for nothing, determine nothing about absolute magnitude of the entropy value from the third law of thermodynamics, which is based on the observation of low temperature chemical reaction. It is concluded that from a third law of thermodynamics, which is based on observation of low temperature chemical reaction. It is concluded that the entropy for all pure substance can be assigned the absolute value of 0 at the absolute zero of temperature. Is so the entropy of all pure substance can be assigned the absolute value of 0 the absolute value of 0 at the absolute zero of temperature. And also follows from the subject of statistical the subject of statistical thermodynamics that all pure substances state that in the ideal gas state at absolute zero temperature have zero entropy. However, when there is no change of composition, as would occur in a chemical reaction, for example, it is quite adequate to give values of entropy relative to some arbitrarily selected reference state, such as was done for earlier when tabulating value of internal energy and enthalpy. From tables, we have H, U, and also S. In each case, whatever reference value is chosen, it will be cancelled out when the change of property is calculated between any two states. This is the procedure followed with the thermodynamic tables to be discussed in the following sections. A word should be added here regarding to the rule of temperature as an integrating factor. We noted in chapter 4 that Q is path function. In the relation for the entropy, reversible, the rule of T, Q is path function, and therefore delta Q is in the inexact differential may be converted to an exact differential by introduction of integrating factor. Therefore, the 1t factor in this relation serve as the integrating factor to converting the inexact delta Q to the exact differential delta Q on T for a reversible process.